All right, folks. Thanks for that reminder. So, for the purposes of the of the podcast, we will. I'll just quickly say again. We're looking at question 5 on page 9 in the study guide, and it's just a matter of formulating the expression for Kc, which is going to be concentration of your products raised to the power of the coefficient divided by concentration of the reactants raised to the power of their coefficients, which in this case is just 1. And we end up with a relatively small number for this, so a number less than 1. And since numbers significantly less than 1 mean that we have a greater concentration of the reactants at equilibrium, which means our forward reaction happens, but not very much. As soon as we start making the products of the forward reaction, those products start reacting themselves and making the backward reaction happen, the reverse reaction happen. And so the reaction proceeds, but not very far. So we end up at equilibrium with a much greater concentration of reactants than products. All right, so moving to page 10, we're going to talk about what happens when we manipulate the situation to change Kc. And there's a number of ways that we can do that. And there's a table at the top of page 10 that you can kind of fill out as we go that will just to understand what the results of these manipulations are going to be. So there are several ways that we can manipulate our equilibrium constant. We can reverse the reaction, talk about what's the equilibrium constant for the reverse reaction. We can double the coefficients or halve the coefficients. We can also have 2 or more reactions that, like a larger reaction that proceeds in stages. And we might have equilibrium constants for the individual reactions, but we want to know what's the equilibrium constant overall for the whole system of reactions. So we're going to go through each one of those. And the 2 parts of the columns in the table, there's nothing special that goes in either one. You can just fill out effect on Kc. This was just in the answer key. This is just like written out, and this is the mathematical version of it, so you don't have to write both. All right, so if we reverse the equation, or if we are looking at the reverse equation, if we have Kc for the forward reaction, but we want Kc for the reverse reaction, we're going to take the reciprocal. We're going to take the inverse of that. So we're basically going to put our original Kc 1 divided by that number. Okay, so if I have if the Kc for my forward reaction under certain conditions is 794, then if I write it out as the reverse reaction, or if you're asked what is the Kc of the reverse reaction, you just take 1 divided by 794, and you end up with a much smaller number, which makes sense because if you think about it, the Kc for the forward reaction is products over reactants. And then all we're doing for the reverse reaction is we're switching these, right? So we're just taking the reciprocal of that ratio. So for reversing the equation, it's just the inverse 1 over Kc. Yeah. Yeah, for the other reaction. Yeah, that's essentially what it is. Yeah. Okay. All right, so for example, here's an equation for the Haber process. And we're given that the Kc is 9.6 at a temperature of 573 Kelvin. What is Kc for the reverse reaction under the same temperature conditions? Yep, 9.6. What you got? Okay. Okay, so it's just 1 over 9.6. Should have gotten 0.104. And again, it kind of makes sense because we have a Kc greater than 1 in the initial case, not a ton greater than 1. It's just, 1, it's just the tens place, or the ones place, but, and therefore the reciprocal is going to be just a little bit less than 1. So that's kind of something to just check in your head as you're doing these things to make sure that it makes sense. All right, if we have to change the coefficients on the balanced equation for some reason, like say we're involving it in some kind of Hess's law situation, something like that, then we're going to use an exponent on Kc. So if we double the coefficients, then we're going to square the equilibrium constant. If we have the coefficients, we're going to take the square root, right? Because the coefficients are the exponents that we're raising the concentrations to. So overall, the overall effect is going to be taking the initial equilibrium constant, either squaring it or square rooting it. Okay. So if we go back to the table, doubling, we would square it. Halving would be square root. And they're not going to ask you anything more complicated than that. Okay. And then the last thing is when we have that system of equations, a system of reactions that are happening in sequence. So we have the first initial reaction and then a secondary reaction and a third reaction that happens afterwards. We are going to take the product of the individual Kcs. Yeah. Because the equilibrium of the first is going to affect the equilibrium of the second. They're not independent of each other in that regard. So you're going to end up multiplying them. Yeah. Yeah, this is for the last one. So it's going to be multiplying. So if we go back to the table, and it's however many you have in the sequence of reactions. Here it says adding together 2 reactions, so C1 times C2. That's a 2. But you could have a whole bunch of a sequence of, however many you want. Think about something like cellular respiration. Like we write it as this one equation, glucose plus oxygen gives us carbon dioxide plus water, but that's not how it actually happens. It's not a combustion reaction happening in our bodies. It's a whole chain of complicated reactions that ends up being equivalent to a combustion reaction, but is a lot more complicated. So if we were looking for a Kc for something like that, we'd have a whole lot of individual steps that we'd have to factor in there. Not that you would really find that would be a super complicated thing. I don't think anyone would find the equilibrium constant for the entire reaction of cellular respiration. That might be too complicated, but somewhere in between might be useful. Okay. So that is our manipulations. It's a very minor thing. Not going to see that much on the test, but it's good to know. Page 11, we're now introducing yet another variable, yet another letter. This is not Q as in heat. This is Q as in the reaction quotient. It's always uppercase Q in this case. And it's basically exactly the same as Kc. You calculate it exactly the same way. The only difference is that these concentrations are taken at a time when the system is not at equilibrium. So say I start the reaction And I know that the system's not at equilibrium because I can see something changing, and I take a sample and I measure the concentrations of the reactants and products before it reaches equilibrium, then I can plug it into the exact same equation that we used to find the equilibrium constant to get Q. So there's nothing different. You set it up exactly the same way, products over reactants. Coefficients become the exponents. But now we're talking about something that is at a particular point in time. So it's a little bit like the tangent line, right? The difference between the tangent line and just taking the average. We're talking about a specific point in time before we get to equilibrium. The reason this is useful is if we have those data that we can take at some point in the reaction, then we can compare Q to K. And we can see where is the reaction going at that time, given those concentrations. So this would be in a situation where we already know the equilibrium constant for that reaction. So we have Kc is a constant. It's going to be the same for that reaction all the time. We throw a bunch of chemicals in a beaker. We measure their concentrations, and we say, which way is this going to go to get to equilibrium? Okay? So essentially, if the concentrations are exactly the same, then the Q is going to be the same as K, and we're going to say it's at equilibrium. So if Q is equal to K, then it's already at equilibrium. Okay? If Q is less than K, then the reaction is still moving towards equilibrium in the forward direction because we're still making products of the forward reaction, making more products than we are reactants. But if Q is greater than K, that means we're moving towards equilibrium, favoring the reverse reaction. Because the goal is eventually to get them to be equivalent, to reach that equilibrium point. Okay. Then Q and K will be equal, yes. All right, I'm going to flip. I have a second slide that's very similar to this, but has a little bit more stuff on it. So what we talk about, the way we talk about it is we talk about, the equilibrium lies to the right or to the left when we talk about is it biased towards the products or biased towards the reactants. And so we can say, is the reaction going to proceed from the point at which we measured the concentrations for Q? Is it going to proceed to the right, meaning in the direction of the forward reaction, or is it going to proceed to the left in the direction of the reverse reaction? Are we going to favor the production of the products, or are we going to favor the reactants? And so it's just a matter of comparing the two numbers, saying if Q is less than C, we're going forward, we're going to the right. If it's greater than C, we're going reverse, we're going to the left. Okay. So there's an example here on the board that's not in your packet. We've got a reaction at a particular temperature, and we know that Kc is 5.1. So here's our Kc, and we take, we throw stuff in, we look at a particular time during the process of the reaction, and we get Q of 4.1. Which direction is the reaction going to go? To the right or to the left? So Q is 4.1, K is 5.1. It's going to the right because Q is less than K. Think about the way those expressions are set up. So the products are on top. The products of the forward reaction are on top, right? And so if Q is less than K, that means we haven't made enough progress towards the products yet. So it's going to continue going towards the product side. If Q is greater than K, it's like we've made too much of our products. We need to go back to the reactant side to balance that out to get to equilibrium. So there's It depends on, we're going to talk tomorrow about disturbing the equilibrium and what direction things are going to go when you disturb the equilibrium to get to the new equilibrium. So yes, like that wouldn't happen necessarily. You wouldn't necessarily have an overshoot if you just dumped your initial reactants in and let it sit there at under the same conditions. Okay, so this will come in a little bit more handy when we get into talking about disrupting the equilibrium. So yes, you're right. You wouldn't generally have the overshoot and then the comeback, but we might have situations where over the course of a process that involves a reaction, we might end up over on this side, and it might push more towards the reactant side. Yeah, good question. All right, so looking, this is example 1 on page 12. So go ahead and calculate Q for the given reaction with the concentrations that are given, and then compare it to the K that the Kc that you're given, and predict whether the reaction is going to proceed to the right or to the left.
Do we write it as Q subscript C?
It doesn't really matter because in this case, yeah, you can write it as Q subscript C, but given that we have K subscript C and we're dealing with concentrations, it's kind of a given that it's. Right, so this is the reaction quotient, meaning what is the quotient of the concentrations at that particular time in the reaction.
Oh, he's squared. I'm stupid. Like, how do you?
Left or right? I've never been up.
So hang on. It's what is it? Q is 4. We'll go south.
Okay, so where's the reaction going to go? Okay. Excellent. Thank you. All right, so, yep.
Would this be the right way to write it?
Yeah, just, yep. Right, so this, the difficulty here, honestly, is, I mean, first it's, reading the question to make sure you've entered all the right numbers with all the right zeros and whatever, but it's really calculator syntax. So make sure that going into the exam, you are comfortable with the calculator you're using and comfortable with parentheses and whatever else you need, because that is where a lot of people go wrong. And that's a stupid way to lose points, right? I don't want you to lose points that way. You don't want to lose points that way. So practice calculator syntax if you need to. But yeah, so we end up with a number that is 4. So Q is 4. Our Kc is 49. So Q is less than Kc. We're going to drive the reaction to the right, favoring the products, right? I'm going to skip example 2. You can do that on your own, and I will post the key to the whole study guide as soon as we're done with the next section. But I want to now go to the exercise on page 13. So again, we've got, and it tells you have non-equilibrium concentrations, and you're given Kc for the reaction at that temperature. So go ahead and calculate Q and figure out which direction the reaction will proceed. So basically the same thing you just did.
Right.
Perfect. Good. All right, so it looks like everyone whose shoulders I'm looking over seems to be getting this just fine. Question? No, that's right. Yep. Yeah. All right, so this is really, again, it's just plugging in the formula, plugging and chugging. So this should be 4.14 Q. And because Q is less than K, it's going to go to the right. Okay. Go ahead and do number 2 if you haven't already. Yes.
Have you heard about the Philly cheesesteak challenge?
I have not.
It's where you check into
A bunch of
first
seniors are
period,
doing it.
and then you get in your car and drive to Philadelphia to get
Buy a
a Philly cheesesteak,
cheesesteak,
and then
and
you
then
have to
come
come
back
back
before
before
seventh
7th
period.
period.
So you can get Mark present from both first and second.
La 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 la. I can't hear you. I do not have any comment on the advisability of driving to Philadelphia to get a cheesesteak.
What's the Philly cheesesteak?
Okay. You check into first period, like you get Mark's present, then you leave school, drive to Philadelphia to pick up a Philly cheesesteak, you have to come back.
I think it's like a Maryland thing.
Because there's no way it's probably like California.
Yeah, well, obviously.
Flies back. Oh,
You can just fly to California, get in and out, and fly back in time.
So maybe the challenge is to figure out what is the furthest place in which you could successfully do the challenge.
Well, I'm talking about it. I'm like, is that just our school? Or is that like a. Like, that's so funny. And then they were talking to the school owner, and they're like, hey, if you mark us present for some period, we'll bring you back a Philly cheesesteak. And I was like, you probably said yes. You did. Yeah, but after 2 hours in the car, if I could drive, I'd do it.
Yeah. Okay.
If you pay for the cheesesteak, I'll pay for the cheesesteak. You know what? I'll pay for the gas on the way back. I'll pay for the gas on the way there.
You gotta check in the first period on Thursday, and seventh period on Friday.
So which way is it going to go?
That's the only thing.
Well, I drove when I moved to Colorado. I drove.
Okay.
Yeah, also, we could get in and out
to
at
Colorado.
You don't have to go all the way.
Yeah, so I drove there for like.
Wait, don't spoil it yet. Don't spoil it. Guys, spoiler alert. You guys get 0.00038.
Yes, but then you round it.
Wise, it's 0.0008.
Okay.
Attention staff and students, that bell, just a reminder to switch over to Titan time. Again, that bell was just a reminder to switch over to Titan time. Have a good day.
All right, guys. So I think looking around, it looks like everybody got this one as well. So we have relatively small q. However, our k is very, very, very small, 10 to the negative 13th. So our q is bigger than k. Our reaction's going to proceed to the left. We're going to make more reactants. Yes. Yeah, that's my sub. Yeah, I don't know where I got that, but yeah, that's just reaction. Yeah. All right, so we're going to leave it there today. Tomorrow we're going to talk about Le Chatelier. It's one of my favorite parts of chemistry, and it's the best part of this topic. So we're gonna do some cool stuff tomorrow.